Hello, my name is Caitlin Chapman, and this is my Lab 6 Magnetic Molasses video report. The purpose of this lab was to observe and collect data on a magnet falling through a tube of aluminum foil, and then to model those interactions in GlowScript and compare the results. And the fundamental principle that we used was Faraday's law, which says that the induced EMF is equal to the derivative with respect to time of magnetic flux, and then the minus sign in the front is Lenz's law, and then that equals the closed integral of the non-Coulomb electric field along its path. And a brief preview of the result that we got: after recording different trials of dropping the magnet through the tube, we got an average fall time of 1.626 seconds, and after creating our computational model in GlowScript, that calculated 1.472 seconds. They were very close. And so on the slide we have a picture of us dropping the magnet in our initial conditions were the system just being our magnet, the surroundings being the aluminum foil tube and the earth, and the mass that we had was 0.046 kilograms. We have our magnetic moment and the dimensions of the tube, which all of these come to play in the GlowScript code. And so as we went through the experiment, we gathered our materials, we dropped the magnet down the tube and recorded the length of time that it took to come out the other side. We repeated it 5 times and then took the average to find the average time, which was 1.626 seconds. And then we measured the dimensions of the tube like we saw on the slide before. This is a picture of our code, and as we go through it, we're just inputting the values that we recorded. Right at the top, we have the dimensions of the tube, and then we're calculating the field, we're creating the bar magnet and putting our initial conditions, calculating the flux, and creating our simulation, and then we can see our results on this slide. And here's the graph that it creates, and then at the bottom it shows the calculation of 1.472 seconds. So that's awfully close to our original recorded average, and we're going to assume that the computational model is probably more accurate due to human error and other things. And so yeah, human error, humans are controlling the stopwatch, and we're probably slower than the actual time that it took to fall through the tube. And also we didn't have any scales in the lab, so our mass is just a rough estimate. And as for the what if questions, we had what if the resistivity of the conductor was reduced as close as possible to 0, how would the dynamics of the falling magnet change? So reducing the resistivity would allow the induced current to flow much faster, therefore increasing the strength of the magnetic field that's induced that is opposing the magnet's motion. So therefore it would take longer for it to get through the tube. And if holes or slots were cut into the tube, that would interrupt that induced current and decrease the field strength or just eliminate it completely, and the field that opposes the magnet's motion would be reduced. Thank you.